So, in the last class we started doing about this control volume approach, and we talked about the K-Epsilon model. So, K and epsilon model, okay, and we defined what K was, which is basically the turbulent kinetic energy, right. So, in a control volume we had to write an equation for K. Basically K was defined as the advection of K, advection or convection of K was defined as dk by dt. Okay. Then there is diffusion of K, which is given by this term. This is basically a constant, as you will find that there are many constants of proportionalities that arises not naturally, and you are taking that epsilon m is much greater than your kinematic viscosity. Okay. So, other way it implies that K diffusion, okay, is through, okay, eddy viscosity only. Once again remember, this is not a viscosity per se, this is some way that we have cast it like a viscosity. Then like any transport equation you will have a rate of production of K, okay, which is given by epsilon m du bar by dy. So, this is basically what we call the eddy shear stress, okay, and this one is the average velocity gradient. Okay. So, this is also can be written as epsilon m into du bar by dy square, okay. Or in other words, if you remember that epsilon m we already wrote it in terms of k to the power of half L du bar by dy whole square. Okay. So, that was the rate of production. Now, similarly there is something called the rate of destruction or dissipation of K, okay, dissipation of K. So, this is akin, the rate of dissipation of K is akin to something like this. So, let us go to the next page to explain this in a little bit more details. Okay, the dissipation rate is like a, when you actually have a fluid packet of some length scale L, right, okay, of some length scale L. Okay, this is, there will be some drag and other things that will act on this fluid package, on this fluid packet. Okay. So, in other words, that drag force will be given by something like CD rho L square, okay, into k to the power of half square, something like that. Okay. So, in other words, the mechanical power that is dissipated, per unit mass, okay, is given as k to the power of half CD rho L square k half square divided by rho L cube. Okay. So, the dissipation itself should be written as something like CD k to the power of 3 by 2 divided by L. So, that is the dissipation. So, how we explain the dissipation? Dissipation like is any pack of fluid which is L, okay, is acted upon by the viscous drag that acts about it. So, this is any blob of fluid which has got a length scale of L. So, the total drag force is given something like that, and the total mechanical power therefore can be written like this. So, the dissipation, okay, will be this particular term. So, essentially what happens is that you have the dissipation. So, this L which we introduced in the last class as one of the variables, which is like was like the mean free path. Okay. So, this L now is related to the dissipation epsilon. So, that is an important thing that we learn out of this. Okay. So, the K transport equation therefore in the boundary layer therefore becomes, if you collect all the terms together, it will be dk by dt okay. So, that is the total K transport equation in the boundary layer. Okay. So, this is the dissipation, production, diffusion, advection. So, you get a total species transport or like a transport equation, okay, of the turbulent kinetic energy K. K is the turbulent kinetic energy TKE, okay, where we get all these terms. Okay. So, this dissipation is therefore some kind of an unknown factor over here. So, because remember we need an equation for K, we need an equation for L. We showed that this can be reduced to an equation for K and epsilon, right, because L is basically related to the epsilon, which is basically the dissipation. So, in order to connect these two quantities, that basically we now have an equation for K. Now, we need another equation for epsilon, basically for the dissipation, basically to close the Navier-Stokes equation. Okay. Just recall that we had terms like this, okay, and this, okay, which we somehow packed it up into epsilon m. Then we kind of try to put the same thing in terms of two other quantities. So, that is the transformation. So, basically this is the unclosed, this was unclosed. Now, these two are unclosed. Out of that one we have kind of closed it by writing an equation for K, right. Then the other term now has to be closed because we need an equation for actually the dissipation. So, let us write an equation for the dissipation also. So, dissipation epsilon is also cast as so, you see a lot of constants which are kind of floating around. Okay. So, Em is basically C mu k to the power of half into L, epsilon is equal to C d k to the power of 3 by 2 by L. This leads to epsilon m should be equal to C mu k square by epsilon. So, you can see this is now reduced to this particular form. Okay. Now, what the equation boils down, you now solve for K, epsilon and epsilon m, basically where epsilon m is related to K and epsilon. Normally, if you look at any commercial software like Fluent and if you do the epsilon K-Epsilon modeling, you will find that C mu will be given something like 0.09, C1 will be 1.44, C2 will be 1.92, sigma k will be equal to 1 and sigma epsilon will be equal to 1.3. These are all constants, okay, which are tweaked. Okay. So, they do actually a good job if you actually deal with plane jets, okay, or with plano shear layer. Okay. So, basically what people do is that they basically hand tune these constants. So, plane jets means say a jet coming out of a 2-dimensional orifice, right. So, that is like a plane jet, right. Okay, a flat slit actually, not an orifice. So, that will be the kind of a plane jet. Then plane shear layer will be if you have a splitter plane, okay, and there are 2 flows on both sides, right. Okay, you will get this kind of a shear layer which will actually develop, right. So, this is called a plane shear layer. Okay. So, in these kind of very canonical flows, so this is a jet, this is a shear layer, this is a mixing problem essentially. Okay. The K-Epsilon model does a fabulous job, okay, in basically finding out certain statistics, right, about the flow field. But again remember that when you did an average of the Navier-Stokes equation, right, okay, and when you modeled these terms using K epsilon and things like that, or Prandtl mixing length model, you are basically not resolving any of the Eddy scales at all, right. So, when we started with turbulence, let me show you this particular plane jet. So, you have got lots of these eddies of different sizes, right. Okay. So, if somebody asks you the question that using K epsilon model, can you predict that how these eddies are going to grow, how they are going to break up into other eddies, okay, what are the nature of these eddies and things like that, those are the questions you cannot answer using this, because you are not resolving anything at all, right. You are operating on a mean flow field, and all the fluctuating and the eddy part of the problem, you are basically hiding it into this K and epsilon equation, right. So, it does not do any good job at all, okay, if you want a more insightful discussion about the nature of the turbulent flow. But however, it can give you good answers regarding, for example, you want to know the shear growth rate, or you want to know certain statistics about the flow field, that it can do a reasonable job. But that also you have to hand tune these constants to meet a particular situation. So, what normally people do will be that they will first do experiments, they will park their model, they will find out these constants, and then they will apply the model around the experimental data space, right. But for example, you cannot use it, for example, in a flow over an aerofoil, for example. Okay. So, you cannot use it blindly, because these equations are all done with this specific sets of constants. Okay. So, you have to be very careful when you are using this kind of turbulence model, they are not universal in nature at all. Okay. Now, in mixing length hypothesis, if you recall, your du by dy square was given as epsilon m square by L to the power of 4, where L was the mixing length. Okay. So, the K generation term, if you look at the generation, that is epsilon into du by dy square, right, which is epsilon m cube by L4, which is C mu cube K to the power of 3 by 2 L cube divided by L4 into epsilon, and the K dissipation will be equal to C d K to the power of 3 by 2 by L. Okay. And if capital L is equal to small l into C d by C mu cube to the power of 1/4, you can write the K generation term as C mu cube divided by C d L to the power of 4 C d by C cube mu 1 by L to the power of 4 into epsilon. Okay. So, therefore, K generation will be equal to K epsilon. Okay. So, in the inner region, of turbulent boundary layer, if you recall what the inner region was, right. So, the K generation, okay, is balanced by K destruction or dissipation. right. So, and so this is one of the most important thing that you can take from here in the inner region only. Okay. So, the K epsilon model, as we said, also implies that epsilon m is much greater than gamma. So, therefore, it is not applicable okay, near the wall okay, or viscous sublayer. Okay. So, what do people do? They use K epsilon with, you will hear this kind of models with enhanced wall function, because you cannot predict the viscous sublayer with the K epsilon model. So, you will use K epsilon with enhanced wall function, okay, and similar stuff like this. Okay. So, that would be the way that people approach most of the problems, okay, that K epsilon model, if you want to do it, okay, you use it with enhanced wall function. So, there will be lots of models, K epsilon, then there will be K omega, okay, there are splattered alarmus model, then of course, there comes the Rans set of models, okay, which is 5 equation models essentially. Then you have the LES and the DNS. DNS is of course fully resolved. LES is some modeled, some resolved. Of all these models, okay, there is nothing that is resolved actually. Okay. So, interesting or not, so whatever models that you are using, and Prandtl mixing length is one above. These are non-algebraic models, because basically you are writing the equations for K and epsilon. Okay. The equations are exact, but how you write the equations and the constants that you use, that depends on the model argument that you are trying to put forward. So, K epsilon, K omega, splattered alarmus, and then Rans, these are all the different types of models that you will find different industries are going to use. You cannot say one is better than the other, 2 equation, then 5 equation, it does not mean that the results become any more sophisticated. It just gives you more constants to basically fine tune your answer. Basically, it is like a control panel where you can have different knobs, and you can basically turn the knobs to match your results with whatever that you are expecting. Okay. So, all of these things requires experimental backing. That means you need to validate it using very stringent experiments. If you do not use experiments, then none of these models are actually good, and it has to match within a certain experimental space. Okay. So, no matter what you use splattered alarmus or K epsilon or K omega or Rans, it does not really matter. You have to use all the models with a pinch of salt, basically, that you have to know that how these models actually work. So, experimental backing or experimental data is of paramount importance for all these models, and they work for specific scenarios, work or are fine tuned for specific problems. So, do not think that they can be used universally. Okay. So, there are no universal models as such. Okay. And when you are talking about experimental data, so you will find, and this is of course not a experimental measurements technique course. So, experimental data, how they can be earned is that these days we have high speed particle image velocimetry. I mean, these are the different types of measurements that can help you. Velocimetry. So, if you take a measurement course, so this can actually go 10 kilohertz and higher. So, you can resolve, okay, many of the turbulence scales. So, that is good. Okay. The advent of cameras also enables you to have both good spatial means the pixels of the camera is essentially what the spatial resolution is all about. So, good spatial resolution and plus temporal resolution. So, you have high speed cameras these days which can get you very high temporal resolution also. So, high speed PIV, then there are systems like LDV, laser Doppler velocimetry, which can also measure. Then you have something called hot wire anemometry. Both of these are point measurement techniques. So, this can give you extremely high temporal resolution, so which is good. Okay, you can get extremely high temporal. All these things are commercially available, so that is a good part. That means these days the experimental measurement techniques has improved so much. All of these now can be used as data for validating many of the turbulent models. Okay, the efficacy of the different turbulent models. Even for LES measurements and things like that, all these can be used. Okay, so that is an interesting tool, right. So, and even for species we have these days high speed PLIF, which is planar laser induced fluorescence. So, this can also go up to high speed these days, which can be used for species and in some cases temperature too. So, scalars basically. So, that also makes the job very important for heat transfer as well as for combustion and these applications, applicability in combustion and in heat transfer, mass transfer too. So, this enables us to once again validate some of the experimental data. Some of the experimental data is used for validation of different models. So, in a nutshell, these are the different techniques about which you can read, but in a nutshell that we are now finishing up the turbulence part of the course. Okay, that we have given you a very bird's eye view of the turbulence spectrum, and we have said a few things which you should take like a gospel. First and foremost, in turbulence, it is basically an initial condition and a boundary condition problem. That is where all the complications arises, and it is the nature of the Navier-Stokes equation, or basically the non-linearities of the Navier-Stokes equation, to amplify small differences and basically to blow them up. Okay. So, and turbulence is also a length scale issue. That is because of the disparity of the length scale between the smallest eddies and the largest eddies, as well as the time scales that are associated with them. It makes very, very difficult for any complicated flow problem to be, or heat transfer problems to be solved, okay, by solving the full Navier-Stokes equation. That means the DNS class of solutions that we are talking about is very, very complicated. Even for very simple geometries, though people have done it with the advent of modern supercomputers, you can actually solve many of these problems using DNS, but that is very limited. And for complicated geometries, particularly in problems where there are a lot of other things, say multiphase combustion, multiphase flows and things like that, you not only have to take care of the flow field, but also of the species and the chemical kinetics and the mass transfer, heat transfer, such a whole gamut of things, and they are intercoupled with each other at various length scales and time scales. So, that makes the job very, very difficult, okay, and it might take a lot of time basically to solve those equations. And that is not physically a very interesting thing. That is because industries or whoever wants to use these data, they cannot do that. It's simply because it takes too much amount of time. It is more than the life cycle of their product probably. So, in those cases, okay, people have sought to understand the problem more from a modeling, from an ad hoc point of view, and that is what we covered throughout the class, that what is eddy viscosity. It originates from the nonlinear terms, but people have thought why not couple it as a viscous term, coin it as a viscous term, and still be able to answer some of the basic questions like what is a wall shear stress, what is the wall heat flux, what is the heat transfer coefficients and stuff like that, how the laminar sublayer will look like. So, it is basically makes people more ingenious, and they have put some thought process that okay, there may be a laminar sublayer, maybe there is a turbulent sublayer, and maybe there is this full blown turbulence outer region, and you can do simple scaling arguments in these two layers and try to find out still that what is the heat and mass transfer rates and things like that. And people have used analogies which we talked about, like Colburn analogy, linking heat and mass transfer with the skin friction coefficient. So, all these things okay, have been able to give you some answer, and they match with some of the experimental data, which is the good part, but it does not give you a complete understanding, and it is very limited to a particular type of application. So, it is very applicable to for very canonical problems. You cannot universally apply it for any problems that you want. Okay. And we also saw that if you make the process a little bit harder, we can go to this K-Epsilon suite of equations, which are no better no worse essentially, but it just gives you a little bit more flexibility in playing with your constants and basically parking your simulation to a particular experimental data set. That is how these things actually proceed, and we are able to get some answers like this heat transfer coefficient and skin friction, which is relevant to the industry because that is all that they want to do. Okay. So, at this point we finished the turbulence. In the next class we are going to look at some of the problems, like some kind of a homework problem in turbulence, okay, and that will wrap up the entire turbulence series, and then we will look at more interesting give a little bit of an introduction to some multi-phase problems in which convection also plays a very important role. Thank you.